Hello, everyone. We've been talking about how we can compare the means of two samples using a two-sample t-test. And now we want to expand a little bit beyond that to talk about how we can compare the means across more than two samples. In this particular video, we're going to talk about why we can't use a series of t-tests to make these comparisons across multiple samples. The example that we're going to work through in this video is a study that compared the body temperature of round-tailed ground squirrels across 3 different experimental temperature treatments. Some squirrels were held at 10 degrees Celsius, or the cold treatment. Some were held at 35 degrees Celsius, or the warm treatment. And some were held at 45 degrees Celsius, and that was the hot treatment. And the researchers measured the body temperature of the ground squirrels exposed to one of these 3 treatments. So how can we compare the means across these 3 treatments then? Or more specifically, why can't we use a series of t-tests to make comparisons across these 3 means? We know how to do this, so why can't we just do a t-test between cold versus hot, cold versus warm, and hot versus warm? The problem is that in this comparison of 3 samples, our null hypothesis is that there's no effect of air temperature on the body temperature of ground squirrels. That is, that the mean body temperature of ground squirrels exposed to cold temperatures was equal to the mean in warm temperatures and equal to the mean in hot temperatures. The alternate hypothesis in this scenario is that there is some effect of air temperature on body temperature, but this could be through a difference between cold and warm, or a difference between cold and hot, or perhaps a difference between warm and hot. So when we perform our comparison between cold and warm, then we're testing the null hypothesis that the mean body temperature of squirrels experiencing cold temperatures is equal to the mean body temperature of squirrels experiencing warm temperatures. When we compare warm to hot, we're testing the null that the mean in warm temperatures is equal to the mean in hot. And finally, when we compare cold to hot, we're testing this third null hypothesis that the mean temperature in cold environments is equal to the mean body temperature in hot environments. So comparing these 3 samples then requires 3 different tests of null hypotheses. Now, this is the situation for 3 samples, but if we move up to a scenario where we're comparing 4 samples, then we would need to perform 6 pairwise tests. Or if we go all the way up to 8 different samples, we're now talking about 28 different pairwise tests. So why is this a problem? Well, it's a problem because when we specify our alpha, or our significance level, what we're saying is that this is the rate at which we're prepared to make a type 1 error and claim that there's an effect when in fact there isn't. And for each time we perform a pairwise comparison, then we have this probability of alpha of falsely rejecting our null hypothesis. So instead of having a single statistical test that we're testing at a significance level of alpha, now we have multiple pairwise tests to test our overall single biological hypothesis. So this gets back to the same problem that we had earlier on when we had multiple statistical tests of the same biological hypothesis. And when we do that, we end up inflating our rate of type 1 error above our stated alpha level. So when we perform 3 statistical pairwise tests to compare the means of 3 different samples, we can then see that instead of testing these effects at an alpha of 0.05, there's actually an overall risk of a type 1 error of 0.12 if we test each of these pairwise comparisons at an alpha of 0.05. And we can see that if we get up to 10 samples with 45 different tests, now we can see that there's a 63% chance that we're going to falsely reject the null hypothesis in one of those tests and conclude that those means aren't equal to one another, even when they are. So we can't perform multiple t-tests then because we want to test a single null hypothesis. But for each of those pairwise tests, 5% of the time we're going to falsely reject the null hypothesis. And as a result, our overall risk across our multiple tests of falsely rejecting the null is going to be much higher than our stated alpha level of, let's say, 0.05. So the answer then is not to perform a series of pairwise comparisons across all of our samples, but to instead test a single null hypothesis using a new approach called an ANOVA. Now, ANOVA is an acronym that stands for an analysis of variance. Now, in an analysis of variance, then, we're comparing sample means across more than two samples. And what we're interested in doing in an ANOVA then is to compare how much variation there is among our group means relative to the amount of variation that we have within each of those groups. Now, don't let this term analysis of variance fool you. This is not a comparison of variances across our samples, but it is in fact a comparison of the means across our samples, just like our two-sample t-test was, but in this case, we're comparing across more than two samples. Now, when we perform an ANOVA then, we test a single null hypothesis that all of the true population group means are equal to one another. So in summary then, although we can use a t-test to compare the means of two samples, when we have more than two samples, we need to use a new approach called an ANOVA. Because if we were to use our two-sample t-test to compare each of the possible pairwise combinations of those multiple groups, we would end up inflating our type 1 error rate, or the risk of falsely claiming an effect when an effect didn't in fact occur. So this is why we need this new approach called an ANOVA rather than performing a series of t-tests to make comparisons across more than two groups.